for lunch is by Koji Imamura from Kumamoto University, and Koji will be talking on the Matroid representations of finite rings. Thanks, Koji.
Thank you for introducing me. I'm Koji Imamura from Kumamoto University in Japan. So first of all, I would like to express my gratitude to the organizers for giving me this opportunity to give a talk. So today, I would like to talk about the Matroid representation of finite rings. So this research was conducted with Keisuke Shiromoto at Kumamoto University. So this is the outline of my talk. So maybe this first introductory section would be too elementary for those who know Matroids very much, but I will remind just in case. So, all right, as is well known, there are many equivalent ways to define a Matroid, but in this talk, I will adapt the circuit axiom. That is, a Matroid consists of a finite set E and a family of subsets of E, satisfying these three conditions. The first condition, empty set cannot be a circuit, and second condition implies the minimality for the circuits, and C3 is the circuit exchange axiom. And in terms of circuits, independent sets are the subsets of E containing no circuit. So this is the example of a Matroid. And in this figure, independent sets are indicated as black letters, and yellow part indicates circuits. And this is not a Matroid, because if we take 1, 2, and 1, 3 of circuits, then there is a unique element contained in both of 1, 2, and 1, 3. But the union of 1, 2, and 1, 3 minus 1 is 2, 3, but 2, 3 and all its subsets are independent. So this does not satisfy the circuit exchange axiom. And uniform Matroid is one of the most typical Matroid. And in terms of circuits, the uniform Matroid can be defined as a Matroid whose circuits consist of all subsets of E whose size is k plus 1. So the Matroid in the previous slide is the uniform Matroid U23, K is 2, and N is 3. And this is also, as well known, Matroid abstracts some properties of linear independence. And we can construct a Matroid from a K by N matrix of a field F. So in this case, we define the circuits by minimal linearly dependent sets. So from this matrix, we can obtain U23. So like this, if a Matroid constructed from some matrix over F, we say that it is F representable. On the other hand, all Matroids cannot always be represented as a matrix over any finite field. For example, considering the problem whether the uniform Matroid U24 F2 representable, we can easily see that U24 cannot be represented over F2, but if the order of the field is at least 3, then it is representable. So those problems are known as Matroid representation. So formally, Matroid representation is the problem to determine whether a given Matroid is representable over a specified or any field. And interestingly, it is revealed by Peter Nelson that almost all Matroids are not non-representable. So whereas Matroids abstract the property of linear independence, there are too many Matroids which cannot be represented over field. So our first purpose is to give some representation using a matrix over finite rings, just as over finite fields. And then we would like to construct whether there are some non-representable Matroids over any finite field, but representable over some finite rings. So to achieve those goals, we studied the independence over finite rings. So in this talk, to simplify the discussion, we restrict ourselves to the ring of integers modulo 4. So So this is why I will introduce the independence over finite rings and define two operations, deletion and contraction, for matrix over finite rings. So in an analogous way to those for matroids or matrices over finite field. Okay, so modular independence is defined by Park in 2009. A set of vectors over Z4 is modular independent, means that any linear relation guarantees all of its coefficients must be 0 over 2. So modular dependent means, of course, not modular independent. And now we try to construct a matroid by almost the same procedure in the case of finite fields. So to define the family C, we replace the condition of linear independence by modular independence. So M of A is a pair of column vectors in a K times K by N matrix over the rings Z4 and the family C. But unfortunately, or as we anticipated, modular independence does not necessarily guarantee that all matrices derive matroids. For example, consider this matrix over Z4. Obviously, the empty set is independent, and each single vector is also modular independent. And 1, 2, and 1, 3 are modular dependent. Indeed, there is a linear relation admitting a unit element 1 as its coefficient. On the other hand, the 2, 3 is modular independent because the linear combination of them, which results in the 0 vector, guarantees that the pair of their coefficients must be 0, 0 over 2, 2. So this is not a matroid, as I explained in the first slide introducing a matroid. So now we define the deletion and the contraction for a matrix over rings. So deletion can be conducted just like a matrix over a field. So A minus E is a matrix, remove the column vector indexed by E from a matrix A. For example, if we want to delete the fifth column, we just remove the fifth column from this matrix. And next, contraction. For the time being, we prohibit the vector consisting of only 2 or 0. This restriction will be relaxed later. Anyway, by this assumption, the column vector labeled by E contains some unit element. So as in the case of fields, pivot on a unit entry of E at first, and then delete the row and the column with the unique unit entry in E. So for example, let A be the previous matrix and consider its contraction by 5. First, pivot on the second entry of the fifth column, and then delete the second row and fifth column. So this is the result of the contraction of A by 5. So analogously to the terminology for matroids, we call a matrix obtained by a sequence of deletions and contractions of A, a minor of A. Now to loosen our restriction on the condition of the column vector indexed by E, consider the case that the column vector labeled by E consists of only 0 or 2. So in the case of that AE is 0, the contraction of E corresponds to the contraction by a loop, so it is not allowed in the case of, just like in the case of finite fields. So we can assume that the column vector labeled by E contains some non-zero element. Then let A0 be the matrix pivoted on a unit entry of E and denote the only row of A0 whose ith coordinate is 2 by A. Then if 2 times A is a linear combination of the other rows in A0, then the matrix A is contractible by E. So since the situation seems a little bit complicated, I will give an example. So let's take this matrix as A0 and consider the contraction by 1, 1. In this case, the row vector A is 2, 1, 1, 0, and multiplied by 2 results in 0, 2, 2, 0. And this can be expressed as a linear combination of the second row and third row. So in this case, we say that A is contractible by 1. On the other hand, considering this matrix, the vector A becomes 2, 1, 1, 1. And in this case, 2 times A is 0, 2, 2, 2, but 0, 2, 2, 2 cannot generate it by 0, 1, 0, 1 and 0, 0, 2, 2. So in this case, we say that A is not contractible by 1. Now we are ready to introduce our results. So we determine the excluded minor for a matrix over Z4 to derive a matroid. Also, we will give some representations of some interesting matroids. So first of all, we made sure that fundamental properties on deletion and contractions holds for our definition over Z4 as well. So let A be K by N matrix over the ring Z4, and let E be an arbitrary element of E. And for a family of subsets of S, for a family S of subsets of E, we denote a correction of minimal member in S by M of S. Then whether M of A is a matroid or not, our definition of deletions and contractions, our definition of deletion is consistent with the definition for matroids. And this is also the case for contraction if and only if A is contractible by E. So, okay, before introducing our general results, we take an example of a non-matroid. So we now demonstrate that this 4 by 8 matrix over Z4 does not derive a matroid. So at first, we delete 2, 4, and 6 from A, and then contract by 3, and then contract by 7. So we can obtain this matrix, but this matrix is permutation equivalent to this one. So this one does not derive a matroid, as I explained before. So we can generalize this observation. So the matrix is the excluded minor for a matrix over Z4 to derive a matroid. I won't go into the details of the proofs, but I will introduce some key idea. So we proved the more general results using only set operation for a family of finite set E and family of subsets of E. We defined deletion and contraction so that they correspond to those 4 matroids. And then we revealed that the family can be a set of circuits of some matroid if and only if it has a minor isomorphic to the correction consisting of only 1, 2, and 1, 3. So this needs only circuits axiom and the operation of deletion and contraction. But its proof is slightly complicated. Okay, finally, I will finish my talk with some examples of some interesting representations over Z4. So 2 matroids above, Matroid and S8, are known as F representable if and only if the characteristic of F is 2. On the other hand, the 3 matroids below, non-Matroid P8 and R8, are known as F representable if and only if the characteristic of F is not 2. So thus, it is obvious that the direct sum of one from above and another from below is not representable over any field. But in the case of Z4, all of them can be represented using those matrices over Z4, and thus we can represent any direct sum of them, just like in the case of fields. Also, AG32 prime and F8 are known as non-representable matroids. So for each matroid, there is some single element contraction results in Matroid and also non-Matroid. That is, they have one minor isomorphic to Matroid and another minor isomorphic to non-Matroid. But using a matrix over Z4 and modular independence, we can represent both of them. And we also found that there is some non-representable matroid over Z4. So Vamos matroid and Vetsiros matroid cannot be represented over Z4. So we could only prove by using the computer search. So matrix over Z4 has a standard form like this. But if we assume that there is some representation using a matrix over Z4, we can see that the matrix has to be of the form like this. So we conducted the brute force search for the matrices over Z4 of the form like this. According to our search, Vamos Matroid and Betsiros Matroid cannot be represented over Z4. So it might be noteworthy that Betsiros Matroid can be represented over F4, so field of order 4. So it implies that F4 representability does not necessarily imply the Z4 representability. Okay, finally we summarize our results. So we gave a matroid construction using a ring. So in my talk, we restricted ourselves to the case of the ring of integers modulo 4, but we can construct a matroid with modular independence. It can be generalized to the case of local commutative rings. So in the case of local commutative rings, for vectors to be modular independent, the coefficients must be belong to the unique maximal ideal. And then the discussion on the derivation and contraction can be generalized to the case of chain rings. So chain rings is local principal ideal in ring. And also we found that there is a unique excluded minor for matrix over Z4 to derive a matroid. And then we represented some interesting matroids using Z4 and confirmed that there are some matroids which cannot be represented over Z4. So that's all of my talks. Thank you for your kind attention.
Questions for Koji? Ricky.
You looked at independence.
Yeah.
Could you do something similar with bases and determinants?
So you mean the maximal modular independent sets?
Yes.
Yeah, it could be, I think the basis corresponds to the maximal modular independent sets. So, sorry, can I?
You mostly thought about circuits to define the matroid. Had you thought about different different descriptions of matroids?
So maybe so to construct a matroid by using the circuits axiom and considering the minimal modular dependent sets. So the basis or independent sets corresponds to the maximal modular independent sets or modular independent sets. So
Okay.
so you mean the circuits axiom which satisfies only C1 and C2 and cryptomorphism to the basis or independent sets?
Yeah. For other settings, you can also possibly consider bases. For example, oriented matroids. You might look at the determinant, but you're looking at sets of or elements in your module. But if you looked at computing determinants, you've not looked at this.
Yeah, not yet.
No.
We haven't yet.
Okay. Thank you.
Yeah, go ahead.
Is there a fast algorithm to determine whether it has a minor equivalent to that one?
I don't think so because maybe it is difficult to determine whether one element is contractible or not. So maybe it takes much time to calculate that whether an element can be contracted from a matrix or not. So.
Okay. Before we thank our speaker again, I'll just give you some instructions for lunch. So we are going to the IBS building, which is thank Koji again for his talk. Thank you.